Yeah, so today we'll do an introduction to AMGM inequality, which is, I guess, the second most standard thing to talk about in the field of inequalities. So, let's see. Yeah, so the AMGM inequality, it says if you have some non-negative real numbers, then the arithmetic mean, the average, is at least as great as big as the geometric mean. So you can kind of see that in general, or you can just read this. So today's class may be a bit shorter than usual just because I've kind of been chronically fatigued for a lot of today. Yeah, so just in case not everyone is familiar, the geometric mean of n numbers is, so with arithmetic mean, it's like you add them and you divide by the number of them. So you add up n numbers, xi, I equals 1 to n, and divide by n. For geometric mean, you take the product of n numbers and you take it to the 1 over nth power, or the nth root, in other words. So the geometric mean of A, B, C is just you multiply them and you take it to the 1/3 power. Just like the arithmetic mean is you add them and you divide by 3. So that's geometric mean. So the AMGM inequality just says if you have some number of non-negative real numbers, then their arithmetic mean is as big as their, at least as big as their geometric mean. So let's prove this in the two variable case. So how might we start with the two variable proof? So in the two variable case, it says, oh, this is bigger than or equal to this. So if I ask a question, feel free to say something in the Zoom chat. You can say it to me, or probably to me is best, but you can also just say it to everyone in the Zoom chat. So I like having some student feedback on if you have questions or if you're able to answer some of my questions. So yeah, let's say we want to prove this. What might be the first thing we want to do to prove it? Okay. Yeah, so I see some suggestions in chat. All of those look good to me. So, I'll just go with any one of them. We don't want radicals and we don't want fractions. So maybe we'll just multiply by 2, get rid of the fractions. And then I don't want radicals, so we could potentially square both sides. So let's do that first. And then, this will become something like this. And then someone says, move everything to one side. So that's fine. And then, so now what? How do we see that this is always true? Yeah, so I see some people, saying, yeah, so we can factor this. Yeah, so this is true by the trivial inequality, which is probably the most important inequality. So the trivial inequality says that if x is real, then x squared is at least 0 for all x in the set of real numbers. So this is a real number, so it's so that's fine. So yeah, so this is true, but we're not quite. Are we done with the proof like this? So when we go from like this step to this step, what we're saying is like this implies this, which implies this, which implies this, which implies this. So if you want to write your proof, you should not start off with the questionable statement of something you're trying to prove that could be true or false. You want to start with the true statement and show that a subset of true statements imply a subset of other true statements. And then that implies a set of another true statements. And so you want to go from like true to true to true to true. And maybe you can combine some true facts. So here, if we just like say, oh, well, this is, maybe this is questionable at the start in its truth value. So you don't want to start off with something questionable and say that implies something else. Because what if this was false to start with? So, okay. So we should start with this is true by the trivial inequality. And we can expand and just reverse all the steps. So I guess here's another question. Well, I'll write some stuff out and plus 2 for AB square root. So where did we use the fact that A and B were supposed to be non-negative, I guess? Because, if I plugged in some negative values, it wouldn't make any sense. For instance, what I mean by that is, if I plugged in, if A is 1 and if B is 1, -1, then this would say 1 plus -1 over 2 is greater than or equal to the square root of I, or like is greater than the square root of -1, which makes no sense since complex numbers are not ordered. You can't put a total ordering on them. So we don't want negative numbers to be in our set of variables. Yeah, so I see some people are saying to me, yeah, when we go from this step to this step, we need to use the fact that A and B are not negative. So that's, if you ever prove something and you didn't use the conditions of the problem, which said that the variables are all non-negative real numbers, then you should be checking your proof to see like, if I didn't use that fact, then, what am I assuming? And is there a flaw in the proof? So yeah, so you can only take the square root of AB if both are positive. And this only becomes positive square root of AB if both A and B are positive. I guess both A and B could be negative here, but then you would have, a negative sign. If A and B are negative, then this would equal something like this. Sorry, that's not what I meant to write. But you get the idea where it should be positives. If we allow negatives, it won't make any sense in a lot of cases. So okay, so this would be a perfectly good proof now for the two variable case. And another thing we should ask is what is the equality case? So when can we achieve equality? Equality case. When can we achieve equality? Yeah, so I see, some of you are saying when A equals B. And the way we can see that is that, at the very first step, we have this is only true by trivial inequality. And under trivial inequality, equality occurs if and only if x is 0. So if and only the thing being squared is 0. So that's when A equals B. And this equality case, it carries out through each line since each line is a direct consequence of the previous line. It's just some algebraic manipulations. Okay. For anyone arriving, I would ask that everyone keep their mics off and their cameras off, unless you are comfortable being on a YouTube video with your camera on, which I would prefer that everyone just keeps their camera off for this class. So, okay, so that proves the two variable case. Before we prove the general thing, let's just see like when is this useful. So there are some problems. Let's see. Yeah. And a lot of inequalities, you'll have to reverse your steps. You have to work backwards to solve it and then reverse your steps to write the proof forwards. So maybe I should type that in a lot of inequalities. You solve it backwards, but write the proof with forwards logic. Okay. So, the classic example of some things like this would be like, let's say you're given the perimeter of some rectangle is or maybe like so, these are some standard problems that you can solve with the AMGM inequality. Yeah. Yeah, so that's a good remark, Sam. So that, a lot of the AoPS forums, like sometimes you'll read a proof and it's totally, unmotivated how they came up with the first line or just, how they came up with it, because many times you have to solve parts of the problems backwards. But when you write it up, you don't show the motivation at all. Unless you're teaching something to someone, then you might want to show some motivation on how to solve it, and then a separate process of how to write it up. Those are in general two, separate processes. So, with the first one, let's just draw a diagram. This would say we have, 2a plus 2b is 12. So yeah, how can we, use AMGM here, I guess. So max AB equals question mark. Well, this is kind of a direct application. We can see a plus, if you divide this by 4, we'll get this is equal, well, let's write it on this side, is equal to 12 over 4, which is 3. And by the AMG inequality, it's greater than or equal to the square root of AB. So 3 is greater than or equal to square root of AB. So 9 is greater than or equal to AB. And can we achieve this? AMGM says, yes, we can. That's when A equals 3 and B equals 3. It's achievable. So when you solve a problem like this, if you ever use AMGM, you should, first apply it to solve the problem. But then you should, for most inequalities, you need to check if like equality can be achieved. Can be achieved. So if equality can be achieved, then you know that there actually exists a rectangle with that maximum possible area. It's a 3 by 3 one. Sometimes you'll get some inequalities where you'll prove something is like bigger than or something or less than something else, but you can't actually achieve that bound. So you could say like, oh, well, yeah, I'm not going to try to come up with an example, but there's lots of those cases. For this one, if you have some square parallelepiped with all right angles, if you're given that all 12 edges add up to 96, so 4a plus 4b plus 4c is 96. Then again, if you want to maximize the volume, you want to maximize a product and you're given a sum of variables is constant. So you can just change this to inequality to AMGM. Max ABC equals question mark. So let's block this off. Then you can just divide by 12, a plus b plus c. The 3 is 8, and that is bigger than or equal to cube root of ABC. So the maximum volume would be 8 cubed. And we can achieve it when all the variables are equal to each other. So that would be when all the variables are 8. So A equals B equals C shows we can achieve the equality case. Shows there exists such a parallelepiped. Okay. So a lot of these problems where you have to maximize some volume given something else is constant, you might consider AMGM. I guess this is worth writing down. When maximizing a product or minimizing a sum, you can consider AMGM. So, given a sum. So these are just some things that you might want to consider. I'll give the handout. Yeah, that's fine. Let me send the handout now, I guess. I was gonna give it at the end, but so I usually give it at the end, but I suppose it's fine to give it now. One sec. So I'm going to ask that, this is for internal use only. So the person who wrote this was Matthew Crawford, and he's given me permission to use it, but he'd prefer that, you don't share widely on the internet or something. So yeah, please don't share the document. If I make the document, I generally am okay with it being shared widely on the internet. But so. Okay, so you should have gotten the email with the handout now. And if, you can feel free to work ahead in the handout if you already know, what I'm currently covering. Can we use our mics? So there's a question, can we use our mics when telling the idea and the solution? Yeah, that's fine. Usually I'll prefer that, maybe I'll call on you, but yeah, you can there's a Zoom function for raising your hand and you can answer out loud if you really want to. The reason sometimes I prefer Zoom chat is that if there's 3 people talking at once, I can't make sense of anyone's what anyone is saying. So, but I generally I prefer having a class where I can see people's faces and hear people's voices. It's just that this will be put on YouTube, so it'd be better to keep your camera off. But if you're fine talking out loud, that's fine by me. Just keep in mind it will be recorded. So, okay, so let's see. So let's prove the AMGM inequality in general now. Actually, you know what? Let's just look at. Yeah, so let's look at number 2 on this part, and then we'll prove the general case. So how can we do number 2? It says like a number plus its reciprocal is greater than 2 for all ordered pairs of x, y positive real numbers. So feel free to type your ideas in chat. This means for all x, y greater than 0. Yeah, so this is kind of just a direct application of AMGM. We just directly apply it to this term and this term. You know, if we divide both sides by 2, this says a number plus another number over 2 is greater than or equal to the product of the numbers, or the geometric mean of the numbers rather. And this is just, this is just square root of 1. So that's 1. So then, you know, you can start off with this statement is true by AMGM and reverse the logic to conclude the other direction. So you would write the proof, you know, like this is true by AMGM. And then, yeah. And then, so we just multiply both sides by 2. Okay, so we should prove it in general, and then we'll look at some problems that use it. So, yeah, so let's prove it for the 4 variable case first. So, you know, how might we, so let's just start on a new page. Proof of AM. So, you know, just in case it's not clear, AM stands for arithmetic mean and GM stands for geometric mean. And you can put the word inequality after it, but people will generally know what you mean. You know, probably the most ubiquitous inequality in math is triangle inequality, like the algebraic form. And maybe the second most ubiquitous is like Cauchy-Schwarz, and maybe AMGM is also up there on the list. And I guess trivial inequality is also like more basic and is technically up on the list. But anyways, so let's do it for the, we already did the 2 variable case, so that's fine. So how can we use the 2 variable case to prove the 4 variable case? So we want to prove that this is true. Greater than 4th root of, so we're going to go over 2 different proofs today, neither of which use calculus. There's also a third proof that uses calculus, but we're not going to do that today. So Pranav says we can group A with B and C with D. Yeah. So, you know, can you specify a bit more detail? So Sam says, apply AMGM for A and B and then C and D. Yeah, so that's the key idea here. So we can, you know, say this is the average of A and B plus the average of C and D, and you average these 2 numbers. So that's, you know, so, you know, all we can use is the 2 variable case, which is identical, I mean, which is like equivalent with trivial inequality, but so this is true. So I guess you could do it from trivial inequality, but this is good just to use the 2 variable case. And then, so if we apply AMGM to this term, so all of these are, you know, non-negatives. These variables are all non-negative. Then this is bigger than this, and this part is bigger than or equal to this. So now what? So we need to show it's bigger than fourth root of A, B, C, D. So by 2 applications of 2 variable AM, GM. Yeah, right. So someone said we should now apply this to, we just apply it on two variable AMGM on these two numbers. So this is bigger than square root of AB times square root of CD. And that's exactly what we want to prove. So it's probably easier just to write like ABCD to the 1/4, but a lot of people in textbooks will write it with the radical sign, so I'll do the radical sign sometimes. Yeah, so we applied AMGM 3 times, once here, and once in this step. And 3 applications of 2 variable AMGM here gave us the 4 variable case. So then, yeah, and let me know if there are questions, because I realize not everyone might be so familiar with this, so I'm going pretty fast for like the people who are very new to this. So feel free to ask lots of questions. So yeah, so how can we prove, let's say, the 8 variable case now, if we only can use the 2 and 4 variable case? So sum A1 to A8, A1, A8 to the 1/8. So Sam says we can use the 4 variable case for the 8 variable case, just like we use the 2 variable case for the 4 variable case. Yeah, so that's exactly the right idea. So, let's just call it ABCD. So we'll have this plus this, like EFGH or something, over this. On the one hand, this is basically the average of all 8 numbers. This is A plus H over 8. And if we use 4 variable AMGM twice on the 2 things I just put in parentheses, then it will be, bigger than or equal to this plus this over this. And then we just use the 2 variable case again. So that's bigger than or equal to so ABCD to the 1/8. So yeah, we can use the 4 variable case and the 2 variable case repeatedly. So by induction, we just repeat this process and prove AMGM for all powers of 2. For all powers of 2. So, for n. So yeah, we can inductively apply this process and prove it for all powers of 2. So yeah, are there any questions on that? Okay, so now we can get up infinitely high, but there's a lot of holes, right? Because the powers of 2 are very sparse among the set of positive integers. So we'd like our induction to cover all positive integers, greater than 1. So, how can we use the 4 variable case to prove the 3 variable case? So prove like this. From this. So this will be the next step. So we'll assume we can use the 4 variable case, but we don't know how to prove the 3 variable case just yet. So is there some way I can modify, this expression to get the 3 variable case? And if you want to say something out loud, that's fine too, because sometimes it might be hard to type what you're trying to say. Okay, so there is a suggestion by Alan, but I don't know if that will work. It seems kind of unlikely if that will work or not. So, the suggestion is we try to use like maybe the middle variable is just b plus c. Well, this would prove. So yeah, this wouldn't work. Because if b plus c equal, let's say 2, there's infinitely pairs of b and c that equal yeah, when you do the product, it won't give the product, so I don't think this will work. I don't think there's a way to get rid of like the asymmetry of it, like the non-symmetry of it, if you have a b plus c term. We want a nice product like a times b times c. So I'm skeptical if this will work or not. Like if we hold b and c, b plus c fixed, whoa, what did I do? I tend to do that sometimes, but I don't know what I'm pressing. Then we can keep b plus c fixed and change the value of b times c. So I think it'd be hard to make that work. So here's a hint. This part is pretty hard. Can we let the fourth variable be equals some function of a, b, c? So like, is there some expression, like, can I express the fourth variable as an expression of the first three? And can I make it as symmetric as possible? I.e., can we make the fourth variable an expression of the first three and try to keep some of the symmetry? Yeah, so let's see. Sam suggests maybe let d equal a plus. So you should put parentheses around your numerators, but I understand what you're trying to say. So yeah, maybe we should try this, right? So by for variable AMGM, so let's make sure our logic is like correct. So by for variable AMGM, we can say that this is bigger than or equal to the, I'll just write it to the 1/4 power. And so let's we can, this is true for all positive reals, right? All non-negative reals, A, B, C, D. So in particular, it's true when D is the average of the first three variables. So we can can let D equal the average of the first three variables. Like it should be true in this very specific case if it's true for all A, B, C, D that are non-negative. Okay. So this is now true. So let's see. Now what does this say? Okay. What can we do from here? So yeah, this is so far a true statement. Let's just focus on the left-hand side. How does it simplify? Yeah. So someone suggests multiply by 12 and add common terms. I don't think that will work, and I'm not quite sure what exactly that means. So yeah, this simplifies to, if I have like 3 test scores, A, B, and C, and I add a 4th test score, that's the average of them, then the average of all the first 3 scores doesn't change when the 4th score is added, right? So when you add another number, which is the average of the 3, and you take their average, it doesn't change the average. So this is just A plus B plus C over 3. I mean, you can work it out algebraically. It's like 3A plus 3B plus 3C over 3 plus A plus B plus C over 3. And then it's like 4A plus B plus C over 12, which is just that. Okay. So yeah, let's see. So, okay. So now the 4-variable case just says something like, this is greater than or equal to, I forgot to plug in D in the previous step. So we should plug in what D is in terms of the other 3-variable. So this will be to the 1/4. And yeah, so now what? Multiply by 12. So there is, so here we have, well, does anyone see, how to finish from here? Like, well, what can we cancel from both sides? So this is like A plus B, this thing to the 1st power. And we also have this thing to the 1/4 power, right? So, so someone suggests apply AMGM to this thing. That's a good thought. And I've gone down that rabbit hole before, but I think we don't even need to do anything extra. Like, if you do that, that's fine. But here, let's just see what happens when we cancel, right? So if we really wanted to, we could take both sides to the 4th power. But let's just cancel out a 4th power of this. So actually, let's just take both sides to the 4th power. So this thing to the 4th power is bigger than or equal to this thing. And then we can just cancel out one of the average of the ABCs, right? So then we just have A plus B plus C over 3. So we cancel out the common term. And that's exactly what we want to prove, right? Now we just cube root everything. And we're allowed to cube root because A, B, and C are non-negative. So we won't flip the inequality sign because neither side are negative. And that's exactly what we want to prove. Check, check, check. Yay. Let's draw a happy person who is like, celebrating. Vote. Yay. Okay. Okay. This is a very distorted drawing. There we go. Okay. So we've proven the 3-variable case. So that's good. So does this work in general? Like, can we always go from n equals k to n equals k minus 1? I think there's nothing special about what we just did, right? So this is a pain to write out, but always, if I know the 8-variable case, for instance, right? That's the 8th letter of the English alphabet. So I can just let the 8th variable equal the average of the other 7. And then we do the same process, and we can use 8 variable AMGM to imply 7 variable AMGM, and then 7 variable AMGM to imply 6 variable AMGM, and so on, right? So, you know, I'm not going to write it out because it's a pain to write out, but you know, you can think about it as an exercise if you want to flesh it out and write out your own solution to this. But you can prove yeah. So the idea is just you let the last variable equal the average of the first n minus 1 variables. And then the exact same cancellation effect will occur. And you can prove, you know, that there's nothing special about 4 to 3 here. We use 4 variable AMGM to prove it for 3 variable AMGM. There's nothing special about the 4 and 3. It works just as fine with n equals k and n equals k minus 1. So generalize as an optional homework exercise if you really want to write out the proof. But it's basically, you know, the same idea. So let's take a very quick side note, which is, you know, this is pretty optional for the class, but basically you can prove, so let's see. So let's say we have this matrix and we take its determinant. So taking the determinant, I can add rows. You can use you can add one row to the another. So I'll add row 1 and row 2 to row 3, and it doesn't change the value of the determinant because really you're just shearing the sides of a parallelepiped or something, and it doesn't change the volume, geometrically speaking. So this will be determinant. And if you don't know determinants, it's fine. But basically, this is the same as the determinant of this matrix. And you can factor out the ABC. So this you can, and that will, so I can factor this out and it becomes the determinant of this matrix, 1, 1, 1. So the vertical bars means determinant of a matrix. And then this you can just compute is A plus B plus C, A squared plus B squared plus C squared, minus AB minus BC minus CA. And this at the very start, if you just compute the determinant directly, is equal to this. So this is times 3. So, you know, this is the easiest way to prove that that this identity holds and how to motivate coming up with it, at least that I know of. So this is just an identity that holds for all A, B, and C, not necessarily positive or non-negative. Okay. And so yeah, you know, how can we use this to show AMGM for 3 variable case? So I'm just gonna exercise. This is a random side note that only works for, I think, the 3 variable case, maybe. Use the above. So if you have any thoughts, put it in the Zoom chat. Which part looks like AMGM? So if you didn't understand the derivation, don't worry about it for now. Just if you multiply this out, you'll see that this is true for all A, B, and C. So it's checkable. I just wanted to motivate how one might think of how to factor it. Okay, so I see some of you are saying this term and this term. That's true. But if this is the geometric mean, then what should the individual terms be? Like if ABC is the GM, what should the AM be? Yeah, so that means the individual variables were A cubed, B cubed, and C cubed. So, the AMGM, so what do we have to show about, so let's write out AMGM and let's rearrange it to part of the equation, right? So it says this is true when A, B, and C are non-negative. So then, we can just multiply by 3 and move all the terms to one side. And this is just the left-hand side, right? So yeah, we need to show exactly. We need to show, like Pranav is saying in the Zoom chat, that the left-hand side is greater than or equal to 0. So what is that equivalent to showing, I guess? Well, we can use this identity, right? So if the left-hand side is greater than or equal to 0, then the right-hand side is also greater than or equal to 0. So we need to show this is greater than or equal to 0. So, okay, so what can we say about A plus B plus C? Is it greater than or equal to 0? Yeah, why is this greater than or equal to 0? Right, so we only need to prove it in the case where all three variables are non-negative, like Vignesh said. So, AMGM, the statement says let all the variables be non-negative. So we only need to consider all variables be non-negative. So if each is non-negative, then their sum is non-negative. So that's fine. Yeah, not necessarily positive. It works even if some or all of the variables are 0. AMGM still holds when all or some of them are 0. So that's why I say non-negative instead of positive. I prefer if the English word was like positive 0 or like positive and 0, but I think that'd be more clear, but whatever. The English word is non-negative, so I'll deal with it. So yeah, this is, this first factor is always non-negative. It's greater than or equal to 0. So how can we prove the second factor is always non-negative? Yeah, go ahead, Pranav.
Yeah, we can write it as a minus b square plus b minus c square plus c minus a square whole divided by 2.
Yeah, so exactly, right. So we want to prove this. If I multiplied it by 2, then I would get exactly this. So if I just divide this by 2, then these two, this expression equals to this expression. So this is a sum of squares. So you have half a square plus half a square and half a square. So by trivial inequality, each of these are non-negative. So the whole thing is non-negative. Okay, great. So that's an alternative proof that AMGM works. So when does equality hold here? Like, so. Well, we know what the answer is supposed to be, but how can we see it from our proof here? So let's see. The only inequality, we need to show the left-hand side is greater than or equal to 0. So that's equivalent to showing the right-hand side is equal to 0. I mean, is non-negative, sorry. Yeah. So equality holds when this thing, when the sum of the three things minus their geometric mean, minus 3 times their geometric mean, is equal to 0, right? So that means the right hand side has to equal. Wait, no. Well, so yeah, so right. So let's see. So either this can equal 0 if so this could equal 0, or the other factor could equal 0, right? So if this equals 0, that means each of the individual squares is equal to 0, which means all pairs of variables are equal, meaning all the variables are equal. So, this is one case of equality when A equals B equals C equals A. That would make the right-hand side 0, which would make the AM equal to the GM. Or, 3 times the sum, AM equal to 3 times the GM. So on the other hand, you could have this part equal 0, in which case it's the trivial case where all three variables are 0. And yeah, of course, if all three are 0, then their arithmetic mean is equal to their geometric mean, I mean. So yeah, so this case is a subset of that case. So this is just fine as the equality case. So this begs the question, like, does this, so there's two questions I want to address here, that are natural to ask. Does this generalize? Like, can I look at this determinant each time? I don't think it generalizes in the two variable case. Yeah, I think this doesn't generalize. Like, is there some 4x4 matrix that I can look at the determinant of to prove the 4 variable AMGM? I don't think it works for 2 variables, so I'm a little skeptical if it works for what's it called, 4 variables. You get some identity that can be factored, but I don't think, yeah, I kind of doubt it works. But that's an interesting thought. So I'm just gonna say I think not, but I'm not sure because I just thought of this. I think not sure. So you should think about it on your own. The other thing that I forgot to mention was in our proof, what was the equality case for, this part? 2 variable implies 4 variable. Like, when can the two sides of an inequality be equal? Right, so right, so Daniel says when all variables are equal, and some other people have said that too. So we should analyze the, like, all we know is 2 variable inequality, right? So this thing is equal to this thing when A equals B. And this thing is equal to this thing when C equals D. So we definitely have A equals B and C equals D. And then this thing is, when we apply AMGM from this step to this step, then, well, we just get that A times B equals C times D. So AB equals CD. So yeah, that means all four variables are equal. A equals B, and the product of the last two equals the product of the first two. So all four variables must be equal. So yeah, so with the two variable case applied 3 times, we get that the equality case occurs when all four variables are equal. And that generalizes to all powers of 2. We should also check when does this have equality case? Like when do we really achieve equality in the AMGM from this proof, I guess. So our proof actually started here. Yeah, so I see someone said this for the earlier question, which was when, let's see, equality occurs when, so yeah, here we're using 4 variable AMGM, and that equality case occurs when all 4 variables are equal. And we set the 4th variable to be the average of the first 3. So yeah, and since we're proving the 3 variable case, if this is true, then, if all 3 numbers are equal, then they're definitely equal to their average. So that's fine. So yeah, that's fine as well. Okay, yeah. If some of you have to go, that's totally fine. This will be recorded, and I'll share the Dropbox and the YouTube link. I'll put it in a Dropbox folder and also share the YouTube link. So, okay. Yeah. So here, let's take. I think maybe it would be good to take a 3-minute break or a 5-minute break. So yeah, today's class might be a bit short since I've been really tired earlier today. So I'm just gonna say we'll resume in 5 minutes. Resume in 5 minutes. So that'll be 8:05 my time, Central US time. Okay, so we can resume. Sorry for the slightly longer break, but it's okay. Okay, let's see. What was I going to talk about? Let's see. Yeah, so I think we checked the equality case and we were able to prove AMGM and check the equality case for all steps. So basically we proved AMGM and we proved it for all variables. So A1 dot 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 to AN is greater than or equal to A1, A2 dot 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 AN. And equality occurs only if and only if and only if all variables are equal. So I shouldn't really put the dots there. Okay. So we should look at some of the problems. Yeah, so I'm just going to ask you guys, how can we see that the first thing, how can we prove number one, I guess? Right, so Sunana and Sam both said we can directly apply AMGM. Yeah, that's exactly right. And a lot of other people are saying that as well. So this will be bigger than or equal to this, and their product is just 1. So yeah, oh, sorry, this over 3 is the arithmetic mean, and we can multiply by 3. So yep, that's true. And it does say A, B, and C are positive, so the condition is met for A and GM. What about for number 2? So maybe you can write this as like, so what did it say again? So if you write some cyclic, it just means you cycle through all the variables. So this means this, and this means this. So we need to prove that this is bigger than or equal to So how might we do this one? It looks a little bit different. Yeah, go ahead, Pranav.
We can apply AM greater than GM on A square and BC, and similarly for other terms.
Yeah, right. So we can't apply AMGM directly to all 6 terms. What we can do is we can think, where might we see a BC term, right? Well, we see a BC term when we square root this term. And there's an A term, and we have an A squared term. So what we can say is that this term, if we pair this term with this term, then by AMGM, this is greater than or equal to like A squared BC. And yeah, that proves that the 2 blue terms on the left is bigger than the blue term on the right. So then, yeah, we just do the exact same thing for the other triples by AMGM. So this kind of cyclic summing is like very, very common in Olympiad inequalities. Yeah, and then we just add these three. We add, and we'll get the result. So yeah. Yeah, so any questions on these two? Okay, what about number 3? See if we can work on number 3, and we'll talk about 3 and 4 in a sec. So yeah, actually for this problem session, I'm going to ask that people whisper your answers to me. So we'll just discuss this one together. But yeah, the long way to do it is, maybe we're not so sure how to get started. What we can try doing is we can just try multiplying things out, right? So if I multiply it out, I'll get something like, so I'll have an x, z, y, and a y, x, z. So there's 2 terms like x, y, z. And then there's 6 terms like x, x, z. So like x, x, z or x, x, y. So we'll have x squared y, x squared z, y. So we'll have all 6 of these terms added together with 2xy, z. So, if we were to multiply it out, we would get the sum of all 7 of these terms. So we have cyclic sum xz plus cyclic sum x squared y plus 2xyz is greater than or equal to, what was the thing we were trying to prove again? 8xyz. And then, so how could we prove this, I guess? Well, let's see, we can subtract away 2 xyz's from both sides. So we'll have this. And then how can we prove this? Directly, I guess. Yeah. So, if we apply AMGM to the left-hand side, this says, so it's 6 times their geometric mean. Let's check how many x's are there. 2x's, 2x's, 1x, 1x. So there's an x to the 6th, and then when we take the 6th root, we'll get an x. Same for the y terms, same for the z terms. So, just apply AMGM with 6 variables. So sometimes this will work. You can just expand out a bunch of algebra and then just directly use AMGM, and it'll work. Relatively weak inequalities can fall to things like that. 6 variables. What Pranav was suggesting at the start was we can actually just say x plus y is greater than or equal to 2 root xy. Y plus z is greater than or equal to 2 root yz. And z plus x is greater than or equal to 2 root zx. And then we just multiply these 3 inequalities. So then we'll get, the product of this, the cyclic product, is greater than or equal to 2 times the cyclic product here. And this just becomes 8xyz, and this just becomes what we want it to become. I mean, it is it is the left-hand side. So yeah, that's the better proof. You just use it, you just do 2 variable AMGM 3 times and multiply the results. Yeah, so Sunana says we can also use 3-variable AMGM. That's true. You know, if you use 3-variable on these 3 terms, you'll get the 3 blue terms are greater than or equal to 3xyz. And then if you use 3-variable on these 3 terms, you'll get that those are also greater than or equal to 3xyz. So, and then you can just add those two. That's fine too. Okay. So there are some other problems that we should talk about. We already talked about 10. But you know, in the interest of time, and because yeah, I don't want to talk too long today. Let's just go over one last proof of AMGM. So I'll call this proof 2 of AMGM. And you can do the problems on your own. This is the better way to think about it, in fact. This is more of a way to think about it than a proof, but it works as a proof. So the key idea here is keep their sum the same and move them closer to each. So let me see if I can work out an example. Okay, so let's say you have 5 numbers, right? I want to prove that the average, so let's say we have like 8, 1, 7, 4, 5. I want to prove that their arithmetic mean is bigger than or equal to their geometric mean. So, you know, maybe let's graph these numbers. So we have one number, which is 8. We have a number 1. We have a number 7. We have a number 4. And we have a number 5, right? So what we're going to do is, let's see. Yeah, sure. I guess that's fine. So let's say I take the numbers 8 and 1, right? Their sum is 9, but if I move them closer to each other while keeping their average or their sum the same, then their product increases, right? So what we can say is like, you know, we want to prove that the AM, you know, so this plus, well, whatever I wrote down over 5 is greater than their product, right? 8. I mean, and this is probably obvious if you just multiply it out and add it up. So this is probably obvious by a simple computation, but what we're gonna do is we're gonna change this sum so that each time we keep the sum the same, but we increase the product. So, you know, let's say I wanna move these two numbers so that they get closer and closer to 5, right? So maybe I'll make the closer one 8 into 5. So if I make 8 into 5, then I have to move 1 up to 4. Because this is subtract 3, this is add 3. So now I still have, so this is like 5 and 4. And then 7, 4, 5. So it's the same sum, but now I've increased the product, right? So the product of 5, 4, 7, 4, 5 is, well, it's less than I mean, it's bigger than the product of the original 5, right? So this product is bigger than the product of 8, 1, 7, 4, 5. Because these 3 numbers still have the same product, but these, the 8 and 1, is definitely less than 4 and 5, right? This is because, if you have a quadratic function, you know, if I move two numbers closer together and keep their sum the same, their product will increase. Like a plus b equals constant, a times b. The closer and closer a and b are to each other, the more we'll achieve equality with AMGM, and the bigger the product will be. Like, if I replace, the better way to think about it is if their average is k. If the average of two numbers is k, then if I add k and subtract a from k, then the further away they are from their average, if a is increased, then k squared minus a squared is decreased, right? So when a goes up, the product goes down. When a is small, these two numbers are closer together and their product is bigger. So when a goes down, k plus a times k minus a goes up, and vice versa. So we can change this to 5, 4, 7, 4, 5, and then change the next. So now we have this number and this number. Let's move the 4 up to 5 and the 7 down to 6. So now we have 5, 5, 6, 4, 5. And then let's move these closer and closer to 5 as well. So now we have 5, 5, 5, 5, 5. So with each of these steps, these 5 tuplets of numbers, their sum stayed the same each time, but their product increased each time. So the product is maximized when the numbers are as close together as possible, meaning that you just, the process we did is we computed the arithmetic mean. The arithmetic mean of these 5 numbers was 5. And then we just gradually moved the numbers one at a time to make one of them 5, and the other one is shifted in the opposite direction, also closer to the arithmetic mean. So yeah, hopefully that makes sense. So each time I get another 5 tuplet of numbers with the same sum, but an increased product. So the product is maximized when all 5 variables are equal. So yeah, that's probably the most intuitive way to think about why AMGM is true. It gives you more insight than the first proof we did. So maybe I should type down, each time we keep the sum the same, the product increases, and at least one more term equals the arithmetic mean of the original n numbers. So that's what we're doing at each step. We just shift 2 numbers so that one of them equals the arithmetic mean, shift the other 2 numbers so that at least one of them equals the arithmetic mean, and so on. Arithmetic mean of all the original numbers. So this is, the most intuitive way to see why AMGM should be true. And you can probably formalize it into a proof as well. Okay. So, I guess this is a good enough stopping point for today. You should work on the problems on your own, though. So I think I'll just stay here and give everyone some time to work on some of the problems. You should have gotten the problems in an email from me. The problems I consider fun are number 7 is cool and number 12 is fine, I suppose. 17 is also kind of cool, I suppose. And yeah, you should try the problems. So I'm just gonna leave this up here for now and give you some time to work on them. we got up to number 3, so you can just start at number 4 if you want, but I'm gonna take a break from talking for right now. Yeah, I will definitely share this PDF. It will be in the Dropbox folder where I'll also have the recording of today. Yeah, I'll definitely make sure everyone has a copy of the notes that I write on each time, in addition to the any problem handout list that I have. So usually this class should be 2 hours, but since it's kind of a free and chill class, I think I'm gonna end it here for the AMGM part of class today. Do you guys have any general questions about proof writing or just solving these kinds of problems in general, or just math in general? We can do a quick question and answer session, and then I'll probably call it for today. So next time, I think we'll do weighted AMGM, and I forget what the other topic was gonna be. We'll definitely do more. We'll definitely talk about weighted AMGM and probably like what's it called? The quad, like QM, AM, GM, HM inequality. Yeah, mean chain inequality. So feel free to ask me some questions. I'm just gonna hang out here for a while, and feel free to keep working on the problems. So there's a question, can we use the cyclic notation shorthand on actual Olympiad? Yeah, that's a good question. You can. You just have to be careful about the 2 types of notation. So like what this means, there's two things. This is a squared b cyclic. It means this. If you write symmetric, it means you do it over all like n times n. So symmetric would be like, if there's 3 variables implied, it would mean a squared b plus a. Oh, sorry. Let me think. Yeah, I think it means this. So this is what symmetric means. So you have to be really careful with this, because if you write symmetric AB, symmetric sum AB, you'll actually get 2AB plus 2BC plus 2CA, because you're doing it all over all like n choose 2 pairs. Cyclic, it just cycles through ABC. So this means you do A with all possible neighbors of A, and then B and all possible like pairs with B, and so on. So for instance, if I had written like cyclic sum ABC and there's 4 variables implied, it would mean just what you think it means. You cycle through all 4 variables. If you write symmetric though, you would have like 4 times, you have more terms than you might want. So if you do symmetric sum ABC and there's 4 variables involved in the problem, then it means like you do it over all 4 choose 3, like, hang on. I think you'll actually have 4 factorial terms. So you'll have something like A, B, C. Yes, here you have 3 factorial terms. Here you actually have 4 factorial terms. You do it over all like symmetries of A, B, C, D. So you have to be careful what you mean, because sometimes you mean neither of these things, right? Like there are very, very good situations. There are many situations where you don't mean either of these two things. Like, yeah, so you just have to be careful what they mean. Because, yeah. Let me see if I can find like where I first read about what they mean. Because I don't feel like I'm explaining it that well. But like you have to know what the symmetric group on n variables are. So basically, it's just like there's 4 factorial permutations of this. So if you have something like a cubed b squared c and d to the 0, then if you do symmetric sum on this, you'll have 24 terms. But even if it's like even if it's just like a, b, c, and there's 4 variables and you do the symmetric sum on them, you'll still have 24 terms. It's just that some of the terms will look the same. So this will probably equal like 6abc plus 6bcd plus, So this on if you imply this on 4 variables, it might not be what you want it to mean. So you just have to be careful about that. This will give you all possible things. This will give maybe what you want. This you have to be careful what it means. Let me see if I can find a handout on that. Let's see. Yeah, so if you read the first page on this link, if you read the first page here, Evan Chen explains it probably better than I do. So, okay, there's a question on 4. Just gonna like, yeah. So the question is basically essentially like, if you know W is bigger than X and Y is greater than Z, are you allowed to multiply it? And yeah, you are. The product of two numbers that are at least as big as X and Z, you're allowed to multiply. So that's fine. So that means on number 4, you can, you can just, so I'm just gonna write down 4. It's like this. And then there's like the R and S and T or something, right? Or QRS, whatever. So times, I don't want to keep pasting it, but yeah, so you have this. So you are allowed to multiply these inequalities. Yeah, you're allowed to multiply the 4 inequalities that look like this. Yeah, that's legal. Because, because this is true, you're allowed to multiply inequalities if they face the same direction and you're multiplying the bigger side with the bigger side and the smaller side with the smaller side, and you keep the direction the same and all of them are positive. If you allow negative numbers, this might not be true. Like with negative numbers, you could have like, and then when you multiply, you'll get like 15 is less than 8, false. So you need these to be positive. But the problem does say positive, so it's probably fine. Yeah, it says positive in the original problem for number 4. But that is something you want to be aware of at the very least. There should be non-negative. Yeah, so we're basically done for today. In fact, I'm probably gonna leave soon because I need to rest up for tomorrow. So yeah, thanks for coming. I'll be posting this video in a Dropbox link and also to YouTube. So yeah, I'll see everyone next week. Okay, yeah, see you guys.